Hi everyone. I wanted to give a quick lesson about matched pairs for those people that were absent on class on February 20th and February 19th. Or anyone that just needs a quick refresher from what we learned so that you can watch it again. We're starting off today with just a quick little page about what matched pairs T procedures are. The first thing is that we want to use it when we compare treatments. We also use two sample T procedures to compare treatments, but the main difference is that with matched pairs, you have one group of subjects that has two measurements each. Or you have a pair. So you want to make sure you pay attention. Is if the data can be paired, then it's going to be a matched pairs procedure. And so we do everything that we did from chapter 9 for one sample procedures, but it's just for the difference between the two treatments instead of for one group at all. So it's really all the same stuff. So I'm going to show you what I mean with this first example. So the first thing that we want to do is anytime you have two lists of data like this, just like with the last problems that we did on the two sample day, you want to just go ahead and in your L1 put all the methods A, then in L2 put all the methods B so that we can be ready. And I just want you guys to go ahead and do that so you can hit pause and do that. I've already done it. All right. Now, when we read this problem, whenever you see two lists of data, you might automatically think two sample, but you really have to read the background to figure out if it's two or one. And so when we read through it, it says two different methods, A and B, of determining the level of contamination were used on each of 10 randomly selected specimens. So on each of 10 randomly selected specimens means that there was one sample with two measurements. That's what's going to make this a paired procedure. And so when you look at the table below, we have one subject specimen here, and then there's two measurements below it. And so this is going to end up becoming a paired procedure. So when it says, is there a significant difference? That's easy for us to know our HA will be a not equal to sign in the mean amount of E. coli bacteria detected by the two methods for this type of beef, provide a statistical justification. So what we're going to do is a paired t-test. And now what we need is first we need to get this into one sample. So we need to turn it into one sample by taking our calculator. I've already put the data into my L1 and L2, and so have you. And so what we do is we go over to L3. That's going to be our third list. And we're going to do method A, which is in L1, so second number 1, minus method B, which is in L2, so second number 2. It's imperative that you have L3 highlighted like my screen shows, and then that you type second number 1 minus second number 2, or else it'll try to put all 10 differences in that first line. So your screen should look just like mine. Okay, so now we're looking through, and we see a couple different differences. Just to make sure you guys know, if we did A minus B, because we did L1 minus L2, then I'd just like you to think about before we get started what all these numbers mean. The first one's negative 0.3, and so that means if A minus B is negative, that means that more contamination detected by method B. And then on the flip side, if A minus B is a positive number, then A detected more. Okay, I just wanted to write that off to the side so you'll understand what all the numbers mean. Now let's get going on A test. P, procedure, paired T test. You want to have this word paired because we have one pair of numbers per subject, or experimental unit, I should say, actually, since it's not a person, per unit. Okay, then we start with our HO and HA. HO, mu, I like to use subscript D. We always do no difference for the null. No difference mathematically. When we have one number, it means 0. And then We already decided this was a not equal to sign. We'll define our mean difference as the true mean difference in the amount of E. coli bacteria detected by the two methods. For this type of beef. Okay, and then I'm going to put in parentheses that we did method A minus method B. It's very important that you show that. All right. If our inequality for our HA was a greater than or less than sign, this A minus B is very important. And so is this description I put to the right. All right, you guys know what's up next. It is assumptions and conditions in our alpha level. So we have random, normal, independent, and alpha. We're looking at the top for random. So we have randomly selected specimens of a certain type of beef. Because this was not random assignment, then my independent is the standard. There are at least 10 times 10, 100 specimens of this type of beef. And then for normal, we have our typical normal population not provided. At least 30 in our sample, there's only 10, so we have to do the box plots. So pay close attention here. I've already done my L3 work like we did. You guys should have done it too. So we're going to hit second y equals, and then make sure only plot 1 is on. Plot 1 on, choose the box plot with the dots, and then second number 3 to turn that into L3 because we only care about the differences now. So zoom 9, and that's my box plot. I'm just going to do my best job at drawing it. It's all right. And then I'm going to say no strong skew or outliers. All right, let's move along to our statistical work. Because this is a one sample t-test, our test statistic is t equals x minus mu over s divided by the square root of n. And you guys need to make sure you write the letter t equals. I've been taking off a lot of points for that on your test that I'm grading. And so just make sure that you don't leave it like this. I need to know what letter you're using. Okay, so to get the x bar, we're going to go to stat, calc, enter, but I want the data for L3. I do not care about L1 and L2 individually. I only care about the differences. So my x bar is 0.29. My S is 0.6297. So I'm going to write t equals 0.29. My mu is 0 from my null hypothesis. Then I have the 0.6297 over the square root of 10. So I can write that down here. Okay. So this came from my summary statistics. Now I'm going to do 0.29 divided by 0.6297 over the square root of 10. It's important to put the denominator in parentheses if you're going to do it all at once. 1.456. All right, last thing for my statistical work is to do the p-value. To find the p-value, I draw a t curve. I put 0 in the middle, and then I find 1.456, shade to the right. We're going to pause for 1 second while I reset my video, and then I'll pick it right back up when I'm finished.